This presentation is called Scanaline's Secrets Revealed. Scanaline, scanned LED measurement technology, is completely different from all the other types of optical measurement systems that we find in industry. This difference allows it to function under conditions that would defeat most any other optical measurement system. We're going to talk about just what these differences are. When you look at a Scanaline emitter, what you'll see is, while it's operating, is a red line of light. Now that red line of light is from an array of light-emitting diodes. What you don't see is that those diodes are actually scanning one at a time. And if I slow the clock frequency way down, we'll see the spot moving along sequentially. Now, when it's in its normal running mode, the clock is a quartz crystal clock that generates a precise frequency that's then counted and decoded and is used to light these diodes sequentially. So what we end up with is a spot of light that moves the length of our emitter, which can be 10 inches, 20 inches, 30 inches, 40, and we've made them 80 inches long. And the velocity of that spot of light will remain constant at 2,000 inches per second, no matter what. It can operate for many years without any maintenance or replacement parts, and that makes it a little different too. Now, the next difference is found in the Scanaline receiver. The Scanaline receiver, although it does have a lens for gathering light, has no focused image of what it's measuring. Here's a Scanaline receiver out of its shell, out of its enclosure, and you can see that it has a cylindrical lens. That cylindrical lens focuses light along a line down to a series of photodiodes, and that array of photodiodes gathers the light from the emitter. Now, we don't ever focus that light into any kind of an image, but just gather it and make sure that we can see all the light that comes from the emitter. Now, if the photodetector diodes are that array is about 2.6 inches long, and because there's no focused image, we don't care where the light falls on that emitter. All we need to do is detect its presence. When an object is to be measured, it's placed in between the emitter and the receiver so as to partially block the light from the emitter to the receiver. We generate a timed logic signal for the light and then no light condition, and from that we can easily compute, because of the constant velocity, the width and the position of the object that we're measuring. With a camera, however, we would have some problems. This image-less method of measuring has some real advantages over a camera-based system. Minor movement, for instance, in a camera will shift the position of the image quite radically on the film or on the photo array that is viewing that image. Any movement of the image position could potentially introduce very large errors. The image inside the camera is typically about 20 millimeters long, and the object that's looking at, in this case, would be a meter long. And if we consider that ratio, we're taking an object about 1 meter long and focusing it down onto an array that's 20 millimeters long. That's about a 50-to-1 magnification, if you will, in reverse, as we're taking that long object and focusing it down into the tiny image. Now, if the image inside the camera moves 1 millimeter, because the camera moved, it will appear to have changed position by 50 millimeters because of that 50-to-1 ratio that we just talked about. So although the camera pixel resolution could provide for exceptional measurement accuracy, the mounting and fixturing requirements to make sure the camera doesn't move or vibrate at all can introduce much bigger errors. As we have just mentioned, resolution, how is it that Scanline, made up of an array of light-emitting diodes spaced 1/10 of an inch apart, can measure down to thousandths of an inch? Why isn't it just like a light curtain where, if you've got diodes spaced at 1/4 of an inch and LEDs at 1/4 of an inch, then your resolution's 1/4 of an inch? Well, in Scanline we do some interesting things. Here again we need to look at the receiver. If we consider our spot of light hidden by the strip that we are measuring, we'll notice that at one end of our detector array we can sort of peer under the edge of that strip. As we peer under the edge of the strip, we're going to see light before all the rest of the diodes in the array. Now, as the array continues to scan out from under the edge, more and more of the photodiodes in the receiver will be able to see the light coming out. They're all tied in parallel, so what we observe is a gradually building level amplitude of signal from the LEDs. And we sample those LEDs. Each time an LED is turned on, they ask the receiver, all right, how bright is that? And then the next one comes on, how bright is that? So what we'll have is a smooth curve that goes from no light at all, the array is completely hidden by our object, up to a point where now we're seeing 100% of the light all the time. And we find that at the point that lies halfway between all the light all the time and no light at all is in fact a very high resolution location of our edge. Now, it's based on time, and what we find is that looking at that time, that point where it drops from to the halfway point, we can resolve to about 5/1000ths of an inch with our 100 mil spacing, and that's 5/1000ths of an inch at its worst. And we do that, we determine that by taking an object of a known width and very slowly scanning it mechanically across the array, across the entire array from one end to the other, taking all the measurements that the Scanline sees as it moves along. And then we put that into a statistics program and we say, okay, what is the standard deviation of readings? And the standard deviation of readings on a 30 or 40 inch array is generally somewhere around 5/1000ths of an inch. So we feel that's our real resolution. Now, because our edge position measurements are based on time rather than on pixel brightness or contrast, we can easily accommodate a uniform buildup of dust or other contaminants on our sensor lenses. The automatic gain control in our receivers will compensate for a 20-to-1 change in amplitude of the received signal from the emitter without any degradation of our accuracy or our readings. There's nothing to wear out or degrade in a Scanline system as long as the enclosures remain intact and the temperature extremes are avoided. We have some systems that have been operating continuously for over 20 years without a failure. If you're interested in Scanline and would like to learn more about the applications we can do and see if perhaps you have an application we might be able to help with, take a look at our website at www.harris-instrument.com or give us a phone call or send us an email. The information will be on the screen. Thank you for watching.